Welcome students to Jnanataranga NEET or CET coaching classes for Engineering and Medical Entrance Examination organized by Pre-University Board of Education, Government of Karnataka. Myself Raghavendra Babu M, and today I'll go with the two topics, electromagnetic induction and alternating current, followed by the synopsis as well as the multiple choice questions related to both topics. First I go with the electromagnetic induction and the synopsis of it. You might have heard about the electric flux in your second PUC electrostatics units itself. I go with magnetic flux in the beginning here. Magnetic flux and electric flux almost to the similar topics. The difference is electric flux deals with the flow of the field lines through a surface, whereas magnetic field flux deals with the flow of the magnetic field lines with the surface. Now, if you go to the first point of it, the total number of magnetic field lines passing normally through an area placed in a magnetic field is equal to the magnetic flux linked with that area. The mathematical equation is the net flux through the surface is phi is equal to surface integral of B dot A, which is equal to BA cos theta. Here theta is the angle between the area vector and the magnetic field. Here area is actually a vector. The direction of the area vector is always normal to its surface. If this is the magnetic field and this is the area vector, theta is the angle between the area vector and magnetic field, then the flux through that particular surface is given by BA cos theta. The amount of the magnetic flux through this surface will be maximum when theta is equal to 0 degree, then flux will be equal to BA. And the amount of the magnetic flux through the surface will be 0 when theta is equal to 90 degree, that shows phi is equal to 0. Next, Faraday's laws of electromagnetic induction. There are two laws here. The first law will explain how the EMF is induced, whereas the second law will give the mathematical equation using which we can able to calculate the induced EMF. The first one, whenever the number of magnetic field lines of force passing through a circuit changes, an EMF is produced in the circuit called induced EMF. The induced EMF persists only as long as there is change or cutting of flux. The actual meaning of the statement is, if magnetic field lines passing through any surface changing continuously with respect to time or with respect to its position, there is an EMF induced. This has been done by Faraday in an experiment called coil magnet experiment, where a magnet has been moved towards a coil, and as a result he got to know that the galvanometer connected across the coil was showing some deflection. That deflection indicates there is some induced current, and the induced current is because of the induced EMF. The second law will give, if that is the induced EMF, then on what factor it depends. It's found that the induced EMF is given by the rate of change of the magnetic flux linked with the circuit, and this is the equation E is equal to minus d phi by dt, where the coil, if it is made up of n number of turns, the EMF induced will be n times the d phi by dt. The negative sign used in the equation is just to indicate the direction of the induced EMF. But the negative sign significance will be explained in another law called as Lenz's law. We have few more formulas to calculate the flux. Flux is given by B into A cos theta. As I said already, theta is the angle between the area vector and the magnetic field. But the flux through a surface changes if either of the three change. Example, if magnetic field is changing, then definitely the product of BA cos theta will change and flux will change. If area vector is changing, definitely the magnetic flux change and EMF will be induced. If theta is changing, that is nothing but the angle between the magnetic field and area, then also the flux will change, and whenever flux changes, we get an EMF. So that way we can write E as minus n into d phi by dt. What is phi there? It is nothing but the change in the flux linked with the coil, where phi 2 is nothing but B2 minus B1 into cos theta. This is if magnetic field is changing but area is constant. In the other way, we have another formula, NBA cos theta 2 minus cos theta 1. If the magnitude of the area is not changing, if the magnetic field is also not changing, if the angle between the area vector and magnetic field changes, still we get the induced EMF. There are a few expressions here. First expression is related to induced current, second expression is related to induced charge, third expression is related to induced power. Once we get an EMF, we know current is always EMF divided by the resistance, and EMF is N into d phi by dt divided by R. But the induced charge is also obtained by taking the product of current into time, I into dt. We know what is I here, it is N by R into d phi by dt. Substitute here, we will get N by R into d phi. If you just compare this equation with the current expression, we don't have time factor here. That shows charge induced in the circuit will be independent of the time. Just look at the statement here. It doesn't depend on time. We don't have time factor in the equation. But if you find out the induced power, power is E square by R, and square this expression of induced EMF, you get one more equation like N square by R into d phi by dt whole square. But here we have a time factor, we have a resistance also. That proves the power induced here, it depends on the time and it also depends on resistance. And as I said in the previous slides, that we have an expression for induced EMF as E is equal to minus d phi by dt, the negative sign significance. So Lenz's law will give the direction of the induced EMF. How it explains the direction of induced EMF? According to the statement, the law gives the direction. So according to this law, the direction of the induced EMF or current in a circuit is such as to oppose the cause that produces it. I'll take a small example here. So if I go with a coil, if there is a coil like this and I have a magnet here, let us say this is the north pole of the magnet, this is the south pole of the magnet. If I am moving the north pole of the magnet towards a coil here, the amount of the magnetic flux linked with the coil will increase. As the flux increases through the coil, EMF will be induced in the coil, but the induced EMF opposes the cause of it. Cause means what? North pole is moved towards the coil and flux is increased, and due to the increase in flux, an EMF is induced. But the induced EMF, it opposes the cause, means it opposes the increase of flux. The increase of flux is responsible for the induced EMF, but once the EMF induced, it induces current. The current will flow in such a direction that it opposes the cause of the increase in flux, or nothing but it opposes the magnet pole north, which is moving towards south. How it is possible? That's possible only if this face of the coil behaves like a north, then this north face of the coil, it opposes the magnet motion towards it. What if the magnet is moved away from the coil? Example, if I am taking the magnet away from the coil, now north pole of the magnet is going away from this coil. As a result, the amount of the magnetic flux linked with this coil now decreasing. When the magnetic flux linked with this coil is decreasing, again an EMF is induced, because according to Faraday's law, whenever we get a change in flux, we always get an induced EMF, and due to the change in flux, we get a current, but that current will again oppose the cause. What is the cause of induced current in this situation? In this situation, the induced current is because of the decrease in flux, and flux decreases because north is moving away. But the induced current should oppose the cause. That's why it has to attract the north pole, or otherwise it has to oppose the magnet motion away from it. That's possible if this face of the coil act like a south pole, which means the coil opposes the cause, or the induced current opposes the cause producing it. If magnetic flux increase is responsible for induced current, it opposes the increase of magnetic flux. If magnetic flux decrease is responsible for the induced current, then induced current will oppose the decrease of magnetic flux. Next, induced EMF is not just only because of magnet motion towards a coil or any other cases. We have few more examples. The first one is motional EMI in loop by generated area. Just look at this. We have cross symbol here. The cross symbol is used only to indicate the magnetic field. So if I put a cross here, that shows magnetic field is acting perpendicular to the paper or perpendicular to the board, but pointing into the paper. If I draw a dot and a circle here around this, that shows again a magnetic field is perpendicular to the plane of the paper or plane of the board, but it is pointing away. But this case, I have considered the magnetic field, which are all cross. That shows the magnetic field is perpendicular to the board, but it is pointing in. I have a conductor here, which is PQ. So that conductor is having some length. This conductor is made to move with a velocity v in a magnetic field. Just look at the direction of the velocity. The velocity direction is perpendicular to magnetic field. After some time here, the conductor is moved from this point to this point. The dotted figure shows the new position of the conductor after some time. We know the distance traveled by the conductor is calculated by the formula of distance is equal to velocity into time. On that basis, the distance has been found v into t. By the time conductor moved from this point to this point here, so it has swept some angle, some area, sorry. The conductor, as it moved from here to here, from this point to this point, it sweeps a certain area. As shown in the figure here, the distance covered by the conductor is v into t. The amount of the area generated is nothing but L into Vt, where Vt is what? Distance, and L is the length. So this is just like a rectangle. You know, area of rectangle is a length into breadth. If breadth is the distance covered by the conductor and this is the length, so it has swept some area. That area is equal to the rectangle area, which is length into breadth. This Vt is indicating the breadth and L is indicating the length. Now the flux linked with this area is given by B into A, where A is LVT. As a result, induced EMF is d phi by dt. If you differentiate this with respect to time, so differentiation of time with respect to time will be equal to 1. Finally, you get BLV, because induced EMF is rate of change of magnetic flux. So BLV or BVL, where B is the magnetic field, V is the velocity, and L is the length of the conductor. Just similar way, we have one more example for the induced EMF. So look at, there is a rod here. The rod is having length, where one end is fixed at point Q, where the other end describes a circle along the circumference, where the radius of the circle it describes is nothing but the length of the conductor, but this conductor is made to rotate in a circle with an angular velocity omega, which is a constant angular velocity. And this is B magnetic field. As I said in the last case, the magnetic field is acting perpendicular to the board, but it is pointing in. When this conductor describes one circular motion in a given time, then that conductor has described some area. The area described by this conductor is nothing but the area of circle, which is equal to pi r square. But r is nothing but the length, so A is equal to pi into L square. If A is equal to pi into L square, then we know that the induced EMF E is given by what is the total flux it describes during one circular motion. That is nothing but total flux is B into A divided by the time taken by the conductor to describe one rotation, which is equal to the time period, because it has completed one revolution and the time taken for it is equal to period. Then magnetic field into area is pi into L square, where L is nothing but the radius of the circle it describes, and period is given by 2 pi by omega. So you can cancel pi and pi here. Finally, you get the expression for induced EMF as half B omega L square. This is also another expression for the EMF induced in the case of a conducting rod fixed at one end, where the other end is made to rotate in the circumference of a circle. So this is the expression for EMF. This is a special case. We'll go to another one, a cycle wheel. Just look at the cycle wheel. It has spokes here. The spoke length is equal to L. What if the wheel is rotated with an angular velocity? This is exactly similar to the previous case. The difference is there was only a one rod which was made to rotate in a circle. Now this is a wheel containing too many spokes. Assume that there are n number of spokes here in that wheel, but as the wheel tends to rotate, due to the flux cutting each metal spoke, it becomes an identical cell. Assume this is one spoke. If it describes one rotation, so that will describe an area equal to pi r square. But as a result, EMF will be developed across these 2 points. But there are several spokes here, and all the spokes have a common point. This is point O. But just look at this example. If each conductor acting like a cell, where these two are the potential endpoints of the cell, then these cells are connected in parallel. What if number of cells, identical cells, connected in parallel? So if number of these cells connected in parallel, the effective EMF produced will be equal to E. That shows all such identical cells connected in parallel, because this is the common point for all the spokes, and these are the points. Even this is also made common. It is nothing like a parallel connection of all the cells, and we get the same expression for EMF here, that is half b omega L square, where omega is 2 pi nu, where nu is nothing but the frequency of rotation. You can write nu is equal to even 1 by t, then omega is equivalent to 2 pi by t. If you look at the final expression, in the final expression we do not have the number of spokes. So here E net is proportional to n power 0. What does it indicate, n power 0? N power 0 is 1. That shows the total EMF induced in the case of cycle wheel doesn't depend on the number of spokes. It mainly depends on the speed with which it rotates. It's actually omega, it's not W. So omega is nothing but the angular speed with which the wheel rotates. Go to the next case, self-induction. The meaning of self-induction here. There is a coil here, a cylindrical coil connected to a battery along with a rheostat and a key. If a key is pressed, then there is an increase in current through the coil. Whenever the current through the coil increases, there is a change in the flux related to coil. How the flux changes? Because of change in current. We all know current is responsible for magnetic field. When current through the coil changes, magnetic field through the coil also changes. Magnetic field linked with the coil also changes. Due to the change in the magnetic flux linked with this coil, EMF will be induced. But remember, the EMF induced is always opposes the cause. Look at the direction of the induced current. This is the direction of the inducing current, which is also called main current. And look at the direction of induced current. So this current and this current, they are opposite. This is according to Lenz's law. Induced current opposes the cause. But this time you can notice the current is induced in the same coil because of the change in current in the same coil. That's why it is called as self. The EMF induced in the same coil or in a coil because of the change in current in the same coil. That's why it is self-induction. But look at the other case. This is when the first case when the key is closed. The second case when the key is open. That means when you switch off the battery or when the key is open. The current through the coil tends to decrease. When the current through the coil decreases, again the magnetic flux linked with the coil decreases, again an EMF is induced. But the difference between this case and this case is here current induced because of the increase in magnetic flux and current induced here because of the decrease in magnetic flux, and the induced current direction in the case of increase in flux, and this is the induced current direction in the case of decrease in flux. So this time the induced current direction is along the direction of the inducing current or the main current. I can indicate this as IM, here IM. You notice the difference. In the first case when the key is closed, inducing current is opposite to induced current. In the second case when the flux is decreasing, inducing current is in the direction of induced current. Next, we have few definitions of self-inductions. So amount of the flux linked with the coil is directly proportional to current. Greater the amount of current through the coil, greater will be the flux linked. N is the number of turns in a coil and Fi is the flux through every turn. If I rearrange this, we get L is equal to N phi by I. And suppose if current is 1 ampere, number of turns is 1, then L will be equal to phi. That shows the coefficient of self-induction. L is indicating the coefficient of self-induction is numerically equal to the magnetic flux linked with the coil when the current through the coil is 1 ampere. So this is the equation according to Faraday's law. E is equal to N into d phi by dt. But you know phi is equal to L into I. If you differentiate phi is equal to L into I, you will get this equation. E is L di by dt. What if the di by dt is equal to 1 ampere per second? Meaning of di by dt is 1 ampere per second means if the current through the coil is changing at the rate of 1 ampere per second. Assume if the current starts rising slowly from 0 to 10 ampere. In the first second it is raised to 1 ampere. In the next second it is raised to 2 ampere. In the third second it is raised to 3 ampere. Just look at the change. In every second the current is changing at 1 ampere rate, and in that case if I substitute di by dt is equal to 1 ampere per second, the induced EMF is equal to L, or I can say L is equal to the EMF induced. With that we can define the coefficient of self-induction is equal to the EMF induced in the coil if the current through the coil is changing at the rate of 1 ampere per second or current in the coil is unity. Rate of change of current is unity. Next, magnetic potential energy. See, whenever current flows through a coil, it is not going to sustain immediately because there is an induced EMF always act opposite to the flow of current. In building a steady current in the circuit, always the voltage we supply or the battery we connect, it is going to do some work. So that means battery has to do some amount of work to set up some amount of current in the coil. The amount of the work done in establishing a certain amount of current in the coil will be stored as magnetic potential energy, which is given by the equation. We have a derivation also, that is integration of 0 to I LIDI. I am writing the final expression. This is the final expression, that is U is equal to half Li square, where L is the self-inductance of a coil or coefficient of self-induction and I is the current. Even that same expression, even it can be expressed as N phi I by 2. We have one more concept similar to self-induction. The other concept is whenever the current passing through a coil or a circuit changes, just look at the difference here. In the previous case, we have a coil connected to a battery, but here we have two coils. One is a primary coil, another one is a secondary coil. But primary coil is connected to an AC source. You know what is AC source? It always generates voltage or current which varies periodically both in magnitude and direction. Look at the other coil, secondary coil. It is nowhere connected to any source. It is connected to load through which I can measure the output. Now, if you change the flux through the primary, how does the flux through the primary changes? Because I am using an AC source. As soon as the AC source is switched on, the current through the coil slowly varies. Because of the variation of the magnetic flux linked with the primary, this is kept very close to it. So as a result, the flux linked with the secondary coil also changes. When current flux to the secondary coil changes, if we have a load here and you use any voltmeter to measure what EMF is induced, you will get this. Suppose instead of this I can use a galvanometer also. As and when the current through the primary coil changes, there is a change in the secondary coil which will induce current here. That current will be indicated by the deflections in the galvanometer. You can use an voltmeter to measure the EMF induced. You can use a galvanometer to show or to know what is the current direction. So the direction of the current will be opposite if the flux through the primary decreases, and as a result secondary coil flux also decreases. The deflections will be opposite in the galvanometer. Similar way, I have defined coefficient of self-induction. We can define coefficient of mutual induction. The only difference you notice here is phi 2 proportional to I1, whereas in the case of self-induction it is just phi proportional to I, because there is the same coil. Current flows through one coil and flux changes in the same coil. But in the case of mutual induction, current flows through coil 1, but the flux change is in coil 2. Similarly, current changes in the coil 1 or coil 2 and the flux changes in the coil 1. That's why the phenomena is called mutual effect. You change the current in primary, you get the induced EMF in the secondary. You change the current in the secondary, you get the induced EMF in the primary. That's why it is called a mutual induction. Look at the equation. N2 phi 2 proportional to I1, that means N2 phi 2 is equal to Mi1. We have an expression here, E2 is equal to minus N2 d phi 2 by dt, and look at this difference here. E2 is equal to minus M into di1 by dt. So there is a rate of change of current in the first coil, we get an EMF in the second coil, and vice versa. Suppose if there is a rate of change of current in the second coil, we get an EMF in the first coil. Next, combination of inductance. See, the combination is just similar to resistances. If you connect two resistors in series, you get the effective resistance as R1 plus R2. Even the inductors behave in the same way. Ls is equal to L1 plus L2, and the parallel combination will be L1 L2 by L1 plus L2. But if these two coils are situated very close to each other, the net inductance is given by L1 plus L2 plus or minus 2M, where M is the coefficient of mutual induction. There is one more relation between M, L1 and L2. If there are two coils having coefficient of self-inductions L1 and L2, and if they are magnetically coupled, then M will be the mutual inductance. It is given by M is K into root of L1 L2, where K is a proportionality constant. Next, we have one more case, that is if a coil is connected to battery, and this is a key. There is growth and decay of current in Lcr circuit. Lcr circuit means if there is an inductance, even along with an inductance, there is a resistance. If I consider R here, this is inductor and this is resistor. Whenever a key is pressed, the current through the coil increases. But the increase in coil is not steady, it is exponential increase. Similarly, when the key is opened, the current through the coil decrease. Even the decrease in coil is not steady, it is exponential. So the amount of the current variation, or the instantaneous current is given by the expression I is equal to I naught into 1 minus e power minus r by L into t, where I naught is the current when the circuit reaches the steady state. You can say this is the maximum current, this is the instantaneous current, R is the resistance, L is the inductance. But what if the key is opened, current slowly start decreasing, then current will be equal to, at any instant it is given by I naught into e power minus r by L into t. So substitute the value of t, so at any instant you can able to find out the current. This is during the decay and this is during the growth. So expression for the current at any instant during the growth and expression for current at any instant during the decay. So I have mentioned the expression here. Just I naught is nothing but the maximum current, which is indicated by Imax, generally represented by the ratio of the EMF to resistance E by R. These are the two graphs as I explained in the previous case. So look at the exponential increase of current when the key is closed. Look at the exponential decrease of current when the key is open. And we have defined one more term which is actually called as a time constant, indicated by the symbol tau. What is this time constant? As the key is closed, current starts increasing at a exponential rate. Suppose if you take a particular value of current which is 63% of its maximum value, the time taken by the current to increase to 63% of the maximum value is called as a time constant, and this time constant is given by a formula called tau is equal to L by R. Similar way, when the key is opened, the current starts decreasing at the exponential rate. Suppose if the current drops to 37% of its initial value or maximum value, then the time measured during that case is again a time constant. So both are actually correct, same, tau is equal to L by R, but you have to consider 63% of maximum value during the growth and 37% of its maximum value during the decay. So in both situations, the measured time is called as a time constant, which is tau is equal to L divided by R. And one more point I have to say, if this is in the case of RL circuit and time constant is L by R, suppose if I connect RC circuit, that is a resistance and a capacitor, we again get a time constant there, and the time constant in that case is the product of R and C, where R is the resistance and C is the capacitance. Next we have an AC generator. AC means alternating current generator. It's an alternator or a dynamo. So I have a diagram here. So the main principle of AC generator is, it's nothing but a conversion of the mechanical energy into electric energy. The principle will be explained in this way. It works on the principle of electromagnetic induction, that is, when a coil is rotated in a uniform magnetic field, an EMF is produced in it. Just look at the magnets N and S. These are the powerful pole pieces of the magnet. A cylindrical magnet is used. We have an armature coil A, B, C, D. So it is connected to two slip rings. This is slip ring 1 and slip ring 2, R1 and R2. Now there are two brushes B1 and B2 which are pressed against the rings, and that is connected to a load through which output can be measured. We have explained in the previous cases that whenever flux through the coil changes, there is an EMF. Just look at the situation here. If the coil, armature coil ABCD, is made to rotate, then that is, rings are also going to rotate here, and as a result of the change in magnetic flux linked with this coil, an EMF will be induced. So the flux linked with the coil at any instant is given by B dot A, which is equal to B into A cos theta. But what is theta here? It is the product of omega into t, and omega is nothing but the angular speed with which the armature coil is rotating. Then if you substitute that, we get BA cos omega t. But we have an induced EMF, it is d phi by dt, rate of change of magnetic flux, and it is minus d by dt of BA cos omega t. As you differentiate, you get minus BA, differentiation of cos omega t is minus sin omega t into omega. Minus minus will become plus. Finally, we have BA omega sin omega t. But this is the equation for the induced EMF if the armature coil is made up of only one turn. But what if the armature coil is made up of n number of turns? I should include one more turn, n BA omega sin omega t. Next, these are all just the explanations. Now the working, as I explained, when the armature coil ABCD rotates in the magnetic field provided by the strong field magnet, it cuts the magnetic field lines. Thus the magnetic flux linked with the coil changes, EMF is set up in the coil, direction of EMF determined by Fleming's right hand rule, and the expression which I have derived, N d phi by dt, NBA omega sin omega t, E naught sin omega t. What is E naught here? I have replaced NBA omega with a symbol called E naught. Here E is nothing but the voltage or EMF. E naught is indicating the peak value of the voltage, because whenever the coil rotates, it has been found that the current or voltage generated in the coil is changing periodically both in magnitude and direction. It is just similar to this waveform. So the EMF of current or current will vary in this manner. If this is the EMF and this is the time, if this is time 0, exactly at t by 4 it reaches peak value. So this is E naught, and after t by 2 seconds it becomes 0. Next in 3t by 4 seconds it reaches minus E naught, the negative maximum. Then in t seconds it has completed its oscillation. So this is similar to a simple harmonic motion equation, y is equal to a sin omega t, where y is displacement, a is the maximum displacement, and omega is the angular speed. Similar way I write E is equal to E naught sin omega t. Just look at the comparison. This is displacement at an instant, this is EMF at an instant. This is maximum amplitude, this is maximum EMF. So that shows the EMF induced here is varying periodically both in magnitude and direction. If this is the EMF, we have expression for current also, that is voltage divided by resistance. It is E naught by sin omega t divided by R, then this will become I naught sin omega t. So these are the synopsis related to the electromagnetic induction. Let us go with the MCQs one by one. The very first question is, Lenz's law is a consequence of the law of conservation of what? So the law, it is actually the consequence of law of conservation of energy. Let me explain first. I'll take a small example. If this is the coil and this is a magnet and this is the north pole and this is the south pole. If the north pole of the coil is moved towards the coil, so this will induce a current, and the current will develop a north pole in this phase. But as the magnet is moved towards the coil here, if it develops a north pole, then work has to be done in pushing the magnet further. The amount of the work done in pushing the magnet against the repulsive force caused by this coil will be converted into energy, and that energy is electric energy. So suppose, imagine a situation, if you are moving a magnet, this is not going to be north, this is going to be a south. Then what happens if the north pole of the magnet is moved and this is going to become a south pole? In that case, the magnet would have attracted easily towards the south pole, no work is done and still EMF is induced. This is clearly the violation of conservation of energy, because to get an EMF, some amount of mechanical energy should be spent. That shows it is clearly the law of conservation of energy. The work done will be converted as electric energy. Yes, the second question, the magnetic flux through a circuit of resistance R changes by an amount of delta phi in time delta t. The total quantity of the electric charge which passing during this time through any point of the circuit. I'll explain it here itself. We have an expression for induced current as EMF divided by resistance, which means 1 by R into d phi divided by dt. But current is also expressed as dq by dt, which is equal to 1 by R into d phi by dt. Cancel dt on both sides, you get dq is equal to d phi divided by R, and this is option number B. dq is equal to d phi by R. Taking the equation of E is d phi by dt, substituting current as dq by dt, and we get finally dq as d phi by R. That shows it is charge induced is not depending on time, it depending on the resistance, it depending on the flux change. Now look at a magnet here. A magnet is falling towards a copper ring. This is a copper ring. If the north pole of the magnet falls towards the ring here. Now the question is, if metallic ring is attached with the wall of a room, when the north pole of a magnet is brought near it, the induced current in the ring will be. Obviously, if the north is moving towards the coil, this face of the coil should act like north pole. to make the coil or the copper ring as north, the current in the copper ring should be in an anti-clockwise direction. I will take an example. If this is the circular coil, and if the current in the circular coil in clockwise direction, that face of the coil will act like south. But if the current in the circular coil is in anti-clockwise direction, then that face of the coil is behaving like north, and if north is moving towards the ring, this has to develop a north pole to opposite according to Lenz's law. That means to make this face of the ring as north, the current should be in the anti-clockwise direction, and that is option C. So this is the north pole. Now a coil is having an area A0. Initially it is placed in a magnetic field which changes from B0 to 4B0. That means area is not changing here, magnetic field is changing, the induced EMF will be. We have EMF is equal to change in flux divided by time, which means here A is not changing, we have B2 minus B1 divided by time, then E is equal to A into, so 4B0 minus B0 divided by time, that is 3A0 B0 divided by T. It's option A. Minus because it is according to Lenz's law. We have one more expression, magnetic flux linked with the coil is 8T square 3T plus 5. So phi is equal to 8T square plus 3T plus 5. You want to find out the EMF induced in the fourth second. E is equal to d phi by dt, that is differentiating this 8T square plus 3T plus 5 with respect to time. You get 16T plus 3. At T is equal to 4 seconds, you have to substitute T as 4, 16 into 4 plus 3. It is 64 plus 3, and EMF is equal to 67 units. This is option C, differentiating and substituting time as 4 seconds. Next, a copper ring is held horizontally and a bar magnet is dropped through the ring with its length along the axis of the ring. The acceleration of the falling magnet while it is passing through the ring is, normally when any object is allowed to fall, it falls freely without gravity. That is, it is equal to the acceleration due to gravity. But what if it is dropped through a ring? There is a ring here. Now what happens to the acceleration? Obviously, if the magnet is dropped here, then through the copper ring which is held horizontally, then this would oppose the motion of magnet. If it opposes the motion of magnet, then the fall of this magnet will not be with an acceleration equal to gravity, it is less than g. This is because of the opposition, because this is going to oppose the motion of magnet, and this will be option B, less than that of gravity. Now in a coil of area 10 centimeter square having number of turns 10, and it is changing at the rate of 10 power 8 Gauss per second, and the resistance of the coil is 20 ohm. What is the current in the coil? There is one extra unit you have seen, it is Gauss. Gauss is actually the CGS unit of magnetic field, and 1 Gauss is equal to 10 power minus 4 ampere per second. Now what is the amount of the current in the coil here? In that case, look at the equation. E by R, N is the number of turns d phi by dt. I will substitute here. N is nothing but 10 into d phi by dt, that is 10 power 8 Gauss. 10 power 8 Gauss is multiplied by 10 power minus 4, and area is 10 centimeter square. It is 10 into 10 power minus 4 divided by the resistance 20. So plus 8 and minus 4 minus 4. This is minus 8 and plus 8 get cancelled, and 10 into 10 100. This is 100 divided by 20, which is 5 ampere. We have a coil of 40 ohm resistance and has 100 turns. The radius is 6 mm, is connected to an ammeter of another resistance 160. If the coil is placed perpendicular to field, 32 microcoulomb of charge flows through it. What is the intensity of magnetic field? We have charge here, we have the resistance here, and we have the radius here. Using the charge, the resistance and the radius, we have to determine the magnetic field. Just look at the steps. We have the charge expression as I did in the last class, Q is equal to d phi by R. So d phi by R means 1 by R into, we have d phi is N into B2 minus B1 into A cos theta. So B2 minus B1 means here B2 is 0, B1 is equal to B, and N is the number of turns. Why it is 160 plus 40? Because there are two resistances 160 and 40, adding them it gives 200, where pi is 3.14, and this is 6 into 10 power minus 3. This is nothing but area of the coil, which is pi r square, where r is the radius 6 mm into cos 0. Now the magnetic field obtained will be 0.565 Tesla. Just look at the formula: number of turns, resistance, the change in magnetic field, the area, and theta is indicating the orientation of the area vector with the magnetic field. There are two rails of railway track insulated from each other, and the ground are connected to a millivoltmeter. What is the reading of the voltmeter when a train travels with a speed of 180 km per hour? So first of all, this velocity is in terms of kilometer per hour. You need to convert this kilometer per hour into meter per second by multiplying it by 5 by 18. So this is going to be 50 meter per second. This is the speed. Given the vertical component of the magnetic field, the vertical component of magnetic field is 0.2 into 10 power minus 4 Tesla, and the rail separation is 1 meter. This is similar to the motional EMF, where B into V into L. This is the magnetic field, and velocity is converted here 180 into 1000 by 3600. See, 180 into 1000 divided by 3600 is similar to 180 into 5 by 18. I just mentioned a shortcut that this velocity can be converted into meter per second just multiplying by 5 by 18. What is this one? This is nothing but the length of the conductor. Finally, you get 10 power minus 3 volt. This is the reading shown in the millivoltmeter. A metal conductor of length 1 meter rotates vertically about one of its ends with an angular velocity phi, and the magnetic field is 0.2 into 10 power minus 4, where what is the EMF developed? This is the situation which I explained in the synopsis, that there is a conductor which has been rotating it with an angular velocity, and that angular velocity is 5 radian per second, where the length of the conductor is 1 meter. The magnetic field will be perpendicular to the plane of the paper, which is equal to B equals 0.2 into 10 power minus 4 Tesla. The induced EMF here, using the formula, half B omega r square. R is nothing but the length of the conductor acting like a radius. Half B is 0.2 into 10 power minus 4. This is R. 5. Omega is actually 5 and R is 1 square. Simplifying this, you get 50 microvolt. There is a thin semicircular ring. Look at the magnetic field here. It is actually cross. If it does not appear, I am just mentioning it. I am just marking cross here. That shows the magnetic field is perpendicular to the board. This is the ring, semicircular ring. What is the effective length of the semicircular ring? This is equal to 2r, and this is falling with a velocity v. Question is, what is the potential difference developed across the ring? A thin semicircular ring, conducting ring of radius r is falling with its plane vertical in a horizontal magnetic induction at the position MNQ. The speed of the ring is v, and the potential difference developed across the ring. So the trite question, we have the actual area it describes is 2r into v. Area it describes means actually we should go with the direct formula. E is equal to BLV. B is the magnetic field, L is the actual length, the effective length is equivalent to 2r. This is the effective length 2r. Then the final expression will be B into 2r into V, and it is going to become 2BRV, and that is the EMF. But the direction, see, the direction of the induced EMF will be found by using Fleming's right hand rule. It is also called as a generator rule. You can use Fleming's right-handed rule to know whether the potential is greater at M or greater at Q. Apply the Fleming's right-hand rule, you get the potential at Q is greater. That shows induced current in the ring must generate field in the upward direction, and Q will be at a higher potential. Now there are two coils having mutual inductance 0.005, and this is the current changes in the first coil according to the equation. I is I naught sin omega t, where I naught is 10 ampere, omega is 100 pi radian per second, the maximum value of the EMF in the second coil. So we have an expression M into di by dt, where M is 0.05, differentiation of that current I is I naught sin omega t. 0.005, differentiation will give I naught omega cos omega t. But we need to find out the maximum value. For maximum value, we have to take cos omega t equal to 1. The equation will be 0.005 I naught and omega, because cos omega t becomes 1 when E becomes maximum. On substituting all these, you get the value as 5 pi. There is a rectangular coil having 300 turns. The average area will be 25. This is length into breadth. The coil rotates with a speed of 50 CPS. It is 50 cycles per second. This is the magnetic field about an axis perpendicular to their field. The peak value, peak is nothing but the maximum value. It can be obtained by a formula E naught is equal to omega n B A, where omega is 2 pi f, that is the angular frequency, number of turns, magnetic field, area. So omega is 2 pi into f. F is nothing but 50 cycles per second. This n is the number of turns, 300. This is magnetic field, which is 4 into 10 power minus 2. A is the area, 25 into 10 power minus 2 and 10 into 10 power minus 2. Actually, it is 25 centimeter into 10 centimeter. If you convert that into SI system, 10 power minus 2, 10 power minus 2, simplification of this will leads to 30 pi volt. There is a simple network, a resistance of 1 ohm, a battery of voltage 15 volt and a coil of 5 millihenry. The network shown in the figure is a part of a complete circuit if at a certain instant the current is I is 5 ampere. So, it is through this is 5 ampere of current and it is decreasing at the rate of 10 power 3 ampere per second. Through the coil, the current is decreasing at the rate of 10 ampere per second. This is nothing but di by dt is 10 power 3 ampere per second. Then what is VA minus VB? For this, we are applying Krichov's laws. This is VA, potential at A, minus because the direction of current, along the direction of current, the potential difference will be minus. That's why it is VA minus IR plus E, because you are going from the negative terminal to positive terminal of the battery, it is plus E minus the induced EMF in a coil is L into di by dt. Substitute this, that is equal to what? The potential at B. You want VB minus VA, then shift A to the right hand side. This is VB minus VA. We have minus IR plus E minus L into di by dt. What is minus IR? We have 5 ampere of current here. 5 into 1, this is minus 5. Plus what is E? It is 15 volt. And L is 5 millihenry, 5 into 10 power minus 3. And di by dt is the current decreasing at the rate of 10 power minus 3 ampere plus 3 ampere per second. Since it is decreasing, you can indicate it as minus. Minus into minus will become plus, because this is decreasing rate of current. Plus 3 minus 3 get cancelled. Minus 5 plus 5 also get cancelled. You get only 15. That's why the potential difference between B and A is 15 volt. Now there is a coil of certain radius has 600 turns, but its self-inductance is 108 millihenry. There is another coil 500 turns. What is the self-inductance? Previously, self-inductance expression is mentioned as L is equal to mu naught N square A divided by L. See, mu naught is the permeability of free space, which is given by 4 pi into 10 power minus 7. A is the area of the coil. N is the total number of turns, L is the length of the coil. Then if you substitute this, the length is directly proportional to N square. If I take L2 by L1, this is going to be N2 by N1 whole square. Now what is N2 here? 500. What is N1? 600 into this L2 is equal to N2 by N1 into L1. This is square. Substituting that, you get 500 by 600 whole square into 108. Cancel these two. This will become 25 divided by 36 into 108. 36 3 times it goes. 25 into 3 will become 75 millihenry. This is how you get. It's based on the direct one, L proportional to N square. There is a circuit here. The bulb will become suddenly bright if. That means if there is a coil connected to a bulb and there is a battery, if you close the key, current will flow through the coil and the bulb will glow. The question is, when do we get the brightness more? Is that the contact is made? if the contact is broken, or in both situations contact is made or broken, or it won't become bright at all. So what is the case? The case is, as you close the key, current flows through it and an induced current will be in the opposite direction. Because the induced current is opposing the main current, the bulb will not glow that much brightness. But if the circuit is broken, the induced current will be along the direction of main current. This is actually main current and this is induced current. Since the induced current and the main current are in the same direction, the bulb will have a sudden brightness at an instant when the contact has been broken. An EMF of 100 millivolt is induced in a coil when the current in another nearby coil becomes 10 ampere from 0 in 0.1 second. The coefficient of mutual induction. We have an expression for mutual induction coefficient as M is equal to induced voltage divided by di by dt. What is the voltage induced here? It is 100 into 10 power minus 3 divided by rate of change of current. Look at the current is changing from 10 to 0 in a span of 0.1 second. So di by dt will be 10 divided by 0.1. Then the mutual inductance will be, so 10 by 0.1 is 100. It is 100 into 10 power minus 3 divided by 10 by 0.1 is also 100. This get cancelled. So M becomes 10 power minus 3 Henry, which is 1 millihenry. So E is M di by dt, 100 milli, M change in current is 10 to 0, the time interval is 0.1, the mutual inductance will be 10 power minus 3 Henry, that is 1 millihenry. Coil of self-inductance 50 Henry joined to the terminals of a battery of EMF 2 volt through a resistance 10 ohm. A steady current is flowing through the circuit. If the battery is now disconnected, the time in which the current will decay to 1 by E of its steady value. This has been explained in the case that if the current increases exponentially, look at the variation of current R by L into T. The question is, if the time is equal to 1 by E, what happens to the value of I? Or at what time, the question is, when the current becomes 1 by E of its steady value, I becomes 1 by E times of its steady value, means I naught, then after what time the current becomes 1 by E times I naught. We have an expression, direct expression is tau is L by R. Let me explain this, how it happens. I is equal to I naught into 1 minus E power minus R by L into T. Put I is equal to I naught divided by E. This is I naught into 1 minus E by R by L into T. Cancel I naught. Take the reciprocal of it. No. You get 1 by E is equal to 1 minus E power minus R by L into T. Okay. See, this is actually related to decay. This is related to decay. So the expression for this is going to be I is equal to I naught into E power minus R by L into T. When current becomes I naught by E, we will write I naught by E is equal to I naught into E power minus R by L into T. Cancel I naught. We have 1 by E is equal to minus R by L, E power minus R by L into T. Now the reciprocal of it is E power minus 1 is equal to E power minus R by L into T. Compare the powers of exponential. We will have minus 1 is equal to minus R by L into T. Then T becomes L divided by R. So this is the time taken by the coil so that the current becomes 1 by E times its steady value, which is also a time constant, L by R. It is 50 divided by 10, that's equal to 5 seconds. Next, mutual inductance between primary and secondary circuits is 0.5 Henry. The resistance of the primary and secondary circuit, just notice this, primary circuit resistance is 20, the secondary circuit resistance is 5 ohm. To generate 0.4 ampere in the secondary coil, secondary current in the primary should change at the rate of. We have an expression here. Induced EMF in the second coil is M into rate of change of current in the first coil. What is the induced EMF? It is product of current into resistance I2 R2 we should consider the resistance of only second coil, and the resistance of the second coil is 4 ohm, whereas the resistance of the first coil, the resistance of the second coil is 5 ohm, the resistance of the first coil is 20 ohm, but this is not used because we are finding the current change in the first coil when we get the current in the second coil. This is I2 R2 is M into di1 by dt. Current in the second coil is 0.4, the resistance of the second coil is 5, mutual inductance is 0.5, and this is the rate of change of current in the first coil. Then di1 by dt, on simplifying this, cancel 5 and 5, you get di by dt is equal to, this is 5, 0.5, 10 times it will go, 0.4 into 10, it is equal to 4 is di1 by dt, which is 4 ampere per second. Now, a coil has an inductance of 2.5 Henry and a resistance of 0.5 ohm. If the coil is suddenly connected across a 6 volt battery, then the time required for the current to rise 0.63 times its initial value, final value. The same as the question number 18, there is a decay, but here the current is increasing up to 0.63 times of its final value, which is similar to I becomes 0.63 times I naught. This is equivalent to the time constant, which is L divided by R. So, what is the inductance? We have 2.5, and what is the resistance? We have 0.5. 2.5 by 0.5 is 5 second. So, option number D. T is equal to tau, which is equal to L by R equal to 5 second. Let us see the next topic, alternating current. It is just the continuation of the electromagnetic induction, because in the last synopsis, the last part of the synopsis, we had electromagnetic induction AC generator. That means a generator which induces EMF changing periodically in both magnitude and direction. We will go to the synopsis of the alternating current first. So, just look at the graphs plotted here. First one is a sinusoidal wave, the next one is a triangular, the next one is a rectangular, fourth one is AC superimposed. But we just concentrate on this. This is the most simplest type of oscillatory motion. It is even called as a simple harmonic motion. It's a sinusoidal wave. Here current and voltage varying sinusoidally with respect to time. Now go to the equation. Same equation which is used in the electromagnetic induction. I is I naught sin omega t, is 2 pi. This is frequency. So I naught 2 pi t by t into t. Voltage V naught sin omega 2 pi, V naught sin 2 pi by t into t. Just look at the graph here. Current or voltage will be 0 when time is 0. Current or voltage will reach maximum when the time is t by 4. Current or voltage will become 0 again when the time is t by 2, and current or voltage will become negative maximum in time 3t by 4, and it completes one variation in a time equal to t is equal to t second. That means current reaches maximum twice in the entire cycle here. So voltage or current reaches maximum once in the first half cycle, again a maximum in the next half cycle. So that shows current or voltage changes periodically both in magnitude and in direction. We have to define some quantities related to this. Peak value, which is nothing but I naught or V naught, because during the variation of current like this, so it reaches the maximum value. This is what we call the peak value of current I naught, and in the negative direction this is minus I naught. Similar way we have E naught and we have minus E naught. The mean square value, the average of the square of the instantaneous values in one cycle is actually mean square, but if you take the root of it, it will become root mean square value, which is I naught by root 2. Because in the entire cycle of AC, there is different EMF or different current at different instants of time. If you square all the instantaneous values and take the mean of it, and taking the root of this is root of the mean of the squares of the instantaneous value. Then RMS, the same thing I have explained. This RMS value is given by I naught by R2, and even RMS value of voltage is given by V naught divided by root 2. Just look at the symbol. I can use V as the symbol for voltage. Even I can use E as a symbol for voltage. It is E naught divided by RMS. Both the symbols can be used. This is V naught and this is E naught. Maximum voltage or maximum EMF. Other quantities are impedance. Just like we have resistance in DC circuits, we have impedance. This is the opposition offered by the AC circuits to the flow of alternating current. That is called impedance. Even the unit for impedance is same, ohm. Reactance. Just like a resistor have a resistance, we have an inductor. Inductor is nothing but a coil. This coil also have resistance. The resistance of the inductor is expressed as reactance. It will be inductive reactance for an inductor. It will be capacitive reactance for a capacitor. So inductive reactance is XL given by omega L. You just see this difference, omega into L. Normal resistance do not depend on the omega or frequency. But XL is the resistance of inductor and XC is the resistance of capacitor. The resistance of inductor is directly proportional to the frequency. The resistance of capacitor is called capacitive reactance, inversely proportional to frequency. But for DC, XC is infinity. DC means direct current. The capacitive reactance becomes infinite. That's why a capacitor offers infinite resistance to the flow of direct current. That is because of the capacitive reactance is infinity. In addition to that, we have admittance. This admittance is quite similar to conductance in the case of DC, because if you take the reciprocal of resistance, you get conductance, which the conductance is indicated by G. Similar way, if we have impedance in AC, then we have a reciprocal of impedance, and the reciprocal of impedance is admittance. Susceptance. The reciprocal of the reactance is susceptance. Just like X is the reactance, its reciprocal is susceptance. Now, inductive susceptance and capacitive susceptance. Now, power. Power in AC circuits. Generally in DC, we have P is equal to V into I. But in the case of AC, power in AC circuit is VI sine omega P. V naught I naught sine omega t. This one, instantaneous power here, yeah, P average is equal to VRMS IRMS cos phi, where phi is the phase difference, because normally in alternating current, I and V do not vary in the similar way. Sometimes I will be leading voltage and sometimes V will be leading current. The phase difference between I and V is given by phi. It is VRMS, IRMS and cos phi. Now, power factor. Power factor is normally given by true power by apparent power. Is indicated by cos phi, and normally power factor is ratio of the resistance to the impedance, that is R by Z. Now, let us take a simple case, a resistor connected to AC source. When a resistor is connected to AC source, the applied voltage is V is equal to V naught sin omega t. The amount of current through the resistance will be voltage divided by resistance, which is V naught divided by R sin omega t. That shows I is equal to I naught sin omega t. That proves that voltage and current vary the same way in the case of a resistor. That shows the phase difference between current and voltage will be 0. That means both V and I are in phase, and cos phi is equal to 1 because power factor is cos phi here. When phi becomes 0, cos phi is equal to 1. In the case of inductive circuit, if you look at the coil here connected to AC source, we have an voltage applied is V is equal to V naught sin omega t. But if you find out the expression for current, current is found to be I naught into sine of omega t minus pi by 2. Just look at the expression for current through the coil and look at the expression for voltage we applied. That shows voltage and current are not in phase, and in this case voltage is leading current by an angle equal to pi by 2. This is the phasor diagram used to show that current here and voltage here, the leading is voltage by 90 degree, or even you can indicate the same thing in this way. Capacitive circuit, capacitor connected to voltage. Look at the expression for voltage applied, look at the expression for the current through it. Now, the current expression is I naught sin omega t plus pi by 2. If this is just omega t, this is omega t plus pi by 2. That means current is leading voltage by pi by 2. You can indicate that by a graph. Say this is I, this is V. Current leads voltage by 90 degree, or you can even plot this type of diagram where I is leading voltage by 90 degree. But what happens to the power factor in this case? Because when phi becomes 90 degree, power factor is equal to 0. Meaning of 0 power factor is there is no power dissipated whenever either a capacitor or a coil is connected to AC source. Suppose if R, L, C, all the three are connected to an AC source. See, look at the voltage across R, voltage across L, voltage across C. In the normal case, the applied voltage is always equal to the algebraic sum of the voltages across inductor, capacitor and resistor. But in the case of AC source, the net voltage we apply is not equal to algebraic sum of VR, VL and VC. It is the vector sum of VR, VL and VC. How to find out the vector sum? Look at the diagram here. I have marked the current diagram first, current direction. We all know that in the case of resistor, the voltage and the current are in phase. But in the case of inductor, voltage will be leading current by an angle 90 degree. But in the case of capacitor, current will be leading voltage by 90 degree. So this is VC here. Voltage will be lagging by 90 degree behind current. Here voltage will be leading. Then in that case, the expression for the current induced is I is I naught sin omega t plus or minus phi. The maximum current is voltage divided by impedance. The resultant voltage formula. This is the formula to be remembered because normal case in series connection of resistors or any other components, net voltage will be always the sum of the voltage applied across the individual components. But in this case, it is the vector sum which is VR square plus VL minus VC whole square. Why it is VL minus VC, why not VL plus VC? Because in the case of inductor, current is lagging. In the case of capacitor, current is leading. That's why one is plus VL, the other one is minus VC. The net voltage will be VL minus VC. Just look at this direction. VL along positive y-axis, VC along negative y-axis. Using this V expression, we can obtain the impedance expression as Z is R square plus XL minus XC whole square, where XL is omega L and XC is 1 by omega C. Now the phase difference, because look at the phase difference here. This is the resultant voltage across the combination and this is the resultant current through the combination. That means still voltage and current are not in phase in an LCR circuit. They have a phase difference. But which is leading here? V is leading current. By what angle? Phi. But is V always leads current in case of LCR circuit? No. If XL is greater than XC, then V will be leading I. But if XL is less than XC, then I will be leading voltage. Now, what if there is only inductive reactance? We have no capacitor, this is the Lcr circuit. What if the reactance is only capacitive? We have only Cr circuit. What if the net reactance is 0? That means XL and XC, if both are same, the net value will become 0. When this XL and XC equal to same, condition of resonance. I'll take an example. We have XL is equal to 2 pi FL and XC is equal to 1 over 2 pi FC. When F is increasing, XL increases. When F is increasing here, XC decreases. If I plot a graph here, this is XL and XC. So with frequency, XL increases whereas XC decreases. At one point, both XL and XC becomes equal. The point where both are equal is said to be the resonance condition, and this frequency is called resonant frequency. Is the condition for resonance. When XL becomes XC, VL also equal to VC, then the total voltage is VR, because V is equal to root of VR square plus VL minus VC whole square. If this get cancelled, then you get only V as equal to VR. That shows when at resonance XL is equal to XC, VL is equal to VC, the net voltage will be only the voltage across the resistor. It is a pure resistive circuit. It behaves as a pure resistive circuit. Now resonant frequency, as I explained, XL is equal to XC, equate them, you get the expression for resonant frequency. So look at the curve, the current in the circuit here. It increases as the frequency change, because XL proportional to F, XC inversely proportional to F. As the frequency increases, the impedance decreases and it reaches minimum, current reaches maximum. Thereafter, further increase in frequency, again increase in Z value, that will reduce the current. Next we have quality factor. Normally in a resonance case, whether the curve is sharp or it is like this. Look at the sharpness of the curve here and look at the sharpness of the curve. The measurement of the sharpness of the curve is actually called as quality factor. It is given by the formula 1 over omega naught R CR, or it is also a standard formula we have 1 by R is root L by C. We have a transformer. Normally transformer is used to transmit power, and a normal transformer consists of a laminated sheets of iron core. To that we have connected two coils. One is a primary coil, the other one is a secondary coil, where to the primary coil we apply an input and through the secondary coil we measure an output. But remember, transformer works only on AC, never on DC, because current or voltage to be varied and transformer will do that job. For AC it is useful. It can increase or decrease either voltage or current, but not simultaneously. Transformer does not change the frequency. There is no electrical connection between the winding. They are linked magnetically. That means this is one turn, this is another one. This is primary and secondary. There is no actual linking between primary and secondary. They are magnetically linked. That means if you pass current through the primary coil, there is a change in the flux in the secondary coil, and accordingly you get an output here. And this is flux through secondary and flux through primary will be same normally if d phi s by dt, because whatever the flux you change in primary, if the winding is done proper, the same amount of the flux change in secondary also, then rate at which the flux change in secondary coil is equal to rate at which the flux change in primary coil. So the induced EMF in the secondary and induced EMF in the primary, it is given by the ratio of number of turns in the secondary to the number of turns in the primary. Even you can write ES by EP as also VS by VP. This ratio is called transformation ratio or turns ratio. NS by NP is ES by EP, or NS by NP is VS by VP. But remember, transformer will never work with 100% efficiency. Whatever the power we transmit, so the same power will not be received at the other end. Always there is a loss. That's why to find out the efficiency of the transformer, we divide the output power by input power multiplied by 100%. Output power is product of output voltage into output current divided by input voltage into input current. VS IS will give output power, VP IP will give input power. So that's how we measure the efficiency. Let us go with the MCQs. We have an expression like I is equal to 4 into cos omega t plus 5 ampere, then the RMS value. We have an expression for RMS value. RMS is equal to I naught divided by root 2. This is the peak value, which is 4 divided by root 2, and 4 is nothing but 2 into 2 divided by root 2. 2 by root 2 is nothing but root 2, that is equal to 2 root 2 ampere. That is option B. This is the option. Can be done like this, I naught by root 2. Next, in an AC circuit, we have 100 sin 200 pi t, the time required for the current to achieve its peak value. So if I plot a graph like this is the variation of current. 0, the peak value will be at t by 4, t by 2, this is 3t by 4, and this is equal to t. At what time it reaches the peak value? T by 4. This is the peak value. Question is the time required for the current to achieve its peak value. If t by 4 is the time to taken by the current to reach its peak value, then let us find out. It takes t by 4 seconds. In the given equation, 2 pi by t is 200 pi. What is 2 pi by t? This one. The angular frequency is 200 pi. Cancel this, you get t as 1 by 100 second. If period is 1 by 100 second, the time will be t by 4. It is 1 by 400 second, because 1 over 100 divided by 4 will be 1 by 400 seconds. Voltage and current in an AC circuit are given by 100 pi t, 5 sin 100 pi t minus pi by 6 and 4 sin 100 pi t plus pi by 6. Just look at the additional phase here. This is minus pi by 6, this is plus pi by 6. They have a phase difference. The phase difference is generally given by delta phi is equal to phi 2 minus phi 1. And what is phi 2 here? Plus pi by 6 minus of what is phi 1 minus pi by 6. It will be equal to pi by 6 plus pi by 6, which will be equal to pi by 3. Which is leading here. Look at voltage is minus pi by 6 and I is plus pi by 6. That shows current leads voltage by 60 degrees. It's option C. Why current leads? Because current is plus pi by 6 and voltage is minus pi by 6. There is a resistance 300, that is R, inductance, that is L 1 by pi, connected to a series, 20 volt and 200 hertz phase angle. Phase angle means tan phi formula we have, that is XL minus XC divided by R. But this circuit is containing R and 1 by pi, so XC is equal to 0. I can just write XL divided by R. Then tan phi, what is XL? 2 pi F into L divided by R. Now if you substitute that, tan phi is omega L, 2 pi F divided by R into L. L is what? 1 by pi. Cancel pi and pi here. 2 zeros get cancelled. 2 into 2 is 4 and 3. It is tan inverse of 4 by 3. In a LR circuit, we have L, it's 0.4 by pi. The value of R is 30 ohm and EMF is 200 volt. 50 cycles per second is nothing but the frequency, 50 hertz. The impedance. Formula for impedance will be Z is equal to root of R square plus XL minus XC whole square. But this is only a LR circuit, then Z should be equal to root of R square plus XL square. XC is equal to 0, no capacitor. So if you use this equation, R square, XL is 2 pi FL square, 2 pi F L square. Simplifying this will give the impedance as 50, but current is voltage by impedance. Voltage is 200, impedance is 50, 4 ampere. Now we have another circuit, AC source, a resistance, a coil having inductance 5 millihenry, resistance 4 ohm and frequency capacitance 50 microfarad. That is C is 50 microfarad. What is the amplitude of current? What do you mean by amplitude? Amplitude is nothing but maximum current, which is I naught. I naught cannot be directly determined. We need to find out IRMS first, and after finding IRMS, we can find out I naught. Let us see how it is done. Now, R value 10 ohm, XL here R square 10 ohm. Impedance formula. Net resistance, XL is omega L, omega is 2000, L is 5 Henry, 10 ohm. X is 1 over omega C, you get 10 ohm. 10 and 10. Z. XL and XC both will be equal here. These two are same. So these two get cancelled. Only the remaining thing is R square, it is 10. The amplitude is maximum value, that is V naught by Z. We know what is V naught here. So V naught is how much? 20, the peak value. Then it is V naught divided by Z. 20 by 10 is 2 ampere. In an LCR circuit, potential difference between the inductance, capacitor and resistance. That is VL, VR and VC. They have given VC as 30 volt, and across the inductance it is given as 60 volt. Across the capacitor they have given 30 and this one is 40. The question is the supply voltage. As I said, it is not the algebraic sum. This is equal to VR square plus VL minus VC whole square. Use this formula, substitute 40, 60, 30, you get 50 volt. Now look at the circuit. Across inductor we have 300 volt. Across capacitor we have 300 volt. But across 100, what is the voltage? The reading of the voltmeter and ammeter. See, you have connected a source of 220 volt where VL is 300 and VC is 300. The resultant voltage is normally given by VR square plus VL minus VC whole square. This case VL is equal to VC, so this is going to be 0. That shows V is equal to root of VR square, which is VR, that is equal to 220 volt. So voltmeter reading will be 220. Now current is equal to voltage divided by resistance, 220 divided by 100, that is equal to 2.2 ampere. It is option C, 220, 2.2. Just look at this, 220 and 2.2. An AC source of angular frequency omega is fed across a resistor R and a capacitor C in series. The current registered is I. If the frequency is changed to omega by 3, 1/3 of its value, then the current in the circuit is found to be halved. Calculate the ratio of reactance to resistance. Options root 3 by 5, root 2 by 5, root 1 by 5, root 4 by 5. At angular frequency omega, IRMS, how do we get this expression? See, IRMS is equal to VRMS divided by root of R square plus XC square. Because this is nothing but Z. IRMS is equal to VRMS divided by Z. It is containing only R and C. That's why root of R square plus XC square. I am substituting it. R square plus XC is 1 over omega C square. That will be equation 1. Suppose if that omega is reduced to omega by 3, then current get reduced to IRMS by 2. Simplifying this, you get another equation, equation 2. Solving equation 1, that is omega by 3 for current IRMS by 2 and omega for current IRMS. If you substitute them, you finally get the ratio of XC by R is root 3 by 5. The only thing is writing the two equations for omega current IRMS, for omega by 3 current IRMS by 2. Simplify them, finally you get XC by R as root of 3 by 5. There is a series LCR circuit. We have 44 ohm, 8 millihenry, 20 microhand. What is the resonant frequency and the amplitude? You know resonant frequency is given by a formula F is equal to 2 pi root of L into C. If you use that, omega is 2 pi F and finally you get omega actually. This is 2500 radian per second. That means resonance frequency is expressed in terms of omega and it is 2500 radian per second. Or if it is expressed only in frequency, then it should be F in terms of F, it should be root of 1 over 2 pi into root of LC, that will be in terms of per second, but it is actually angular frequency at resonance. Then the resonance current is voltage by resistance. Why only R? Why Z is not considered? Because at resonance, Z is equal to root of R square plus XL minus XC whole square. This is the actual formula. But at resonance, you must know that XL and XC both will be equal. Then Z will be equal to only R. Hence, voltage by resistance 220 by 44 is 5 ampere. For a series RLC circuit, R is equal to XL. That means I can take XL is equal to R. R is equal to 2XC. If R is equal to 2 times XC, then shows XC is equal to R by 2. So XL is R and XC is R by 2. Then what is the impedance? We have an impedance formula. Z is equal to root of R square plus XL. XL means what? R square minus XC square. XC square is what? R square by 4. What do you get? Root of R square. R square minus R square by 4 is 3R square divided by 4. So you get 4R square plus 3R square. Simplification is done here. See R square plus R square by 4. This one, not 3R square. Just a minute. Yeah. R square XL minus XC whole square. The difference is XL minus XC, it's not the square. It's not the square. It is actually XL minus XC, R minus R by 2 whole square. So this is going to be R square by 4. Now R square plus R square by 4 is square root of 5 R square by 4, which is going to become root of 5 R by 2. But tan phi is XL minus XC divided by R. Then tan phi, XL is what? R. XC is R by 2 divided by R. Then finally tan phi is equal to R by 2 divided by R. This get cancelled, you get half. I think this is option B. So R by 2, XL minus XC, R minus R by 2 by R becomes half. Then substituting R square, XL minus XC, R minus R by 2 is R by 2 whole square, R square by 4, simplification. 100 volt is applied across coil, 1 ampere flows. When 200 volt AC is applied for a 50 cycle per second source, 0.5 current flows. What is the impedance? We know for DC, R is equal to V by I. But for AC, Z is equal to V by I. Here V is 100 and current is what? 0.5. 100 by 0.5 is 200. This is for DC. This is for AC. For DC we have resistance, for AC we have impedance, and I have taken the voltage of AC and I got the current of through AC. Now there is one more circuit here, 30 ohm, 25, 25. So XL, XC are same. What do you mean by this? XL, XC equal means the circuit is in resonance. If it is in resonance, then the total voltage across the combination is the voltage across resistance. The voltmeter reading here is between XL and XC. The voltage across XL and the voltage across XC will be equal but opposite. The net voltage will be VL minus VC 0. So this V will record 0 volt. But ammeter reading. Ammeter is nothing but current IRMS. It is total voltage divided by the total impedance. But resonance means XL is equal to XC is V divided by Z is equal to R. Then IRMS is V is 240, Z is 30, then 240 by 30 is 8 ampere, which is option D. Look at this, voltage across VL and VC, they are equal and opposite, hence voltmeter reading 0, resistance 30, XLXC 25, the current is equal to 8 ampere. There is an oscillator circuit consists of an inductance 0.5 millihenry, capacitance 20 micro, resonant frequency is F is equal to 2 pi root of LC. We have L and C. Substituting L and C in the equation, we get the frequency and the simplification done here. 2 pi root LC, 2 into pi, 5 into 10 power minus 4, it is C. Simplification gives 1592. There is a graph which is having I and E. We have E naught sin 100t, where E naught is the peak value, sin 100t. Then it is observed that the phase difference is pi by 4. Just look at this current and E. Which is actually leading? Current is leading EMF by an angle pi by 4. In which case current leads EMF? Current leads EMF only in the case of capacitor. That means this circuit might be a capacitor RC, that is RC circuit. It actually they have mentioned as RC or LC, but here it is only RC, not LC, because current is leading. In the case of LC, it's different. If it is RC, if it is RL, voltage will be leading, but RC, current will be leading. It should be RC combination. If you look at the 4 options here, RC combination we have 2 options, RL combinations we have 2 options. So this cannot be there. If you look at the 4 options, we have RC combinations 2 options, RL combinations 2 options. This cannot be the 2 options. The only options left is these 2. RC combination option 1, RC combination option 2. We have to choose among these first and second. How it is done? Just look at the explanation. As current leads voltage by pi by 4, and in RC circuit tan phi is XC by 4. Because there won't be any XL with only XC by R. But phi is pi by 4, so tan pi by 4 is 1 over omega CR. That shows tan pi by 4 is 1. So omega CR is equal to 1. As omega is 100, how do you know that omega is 100 radian per second? It is shown in the equation. That's why we can take 100 as omega, then CR will be 1 by omega, that is 1 by 100. So that CR product is equal to 0.01. So check the 2 options. For which 2 combination we have CR product as 0.01? It is only for option A. Because in option A, we have 1 kilo ohm as resistance, we have 10 microfarad for capacitance. Take the product of this RC, it will be 10 into 10 power plus 3, 10 into 10 power minus 3, 10 into 10 power minus 3 is 10 power minus 2, it is 1 by 10 square, it is nothing but 1 by 100. This is what RC value. So that's why CR value 1 by 100 and option A will be correct. Now, coefficient of induction of a choke coil is 0.1 Henry, that is L. The resistance is 12. If it is connected to AC source of 60 Hertz, power factor. See, as I gave the expression for power factor is always R divided by Z. But we have choke and a resistance here. That's why it should be R divided by root of R square plus XL square. But what is XL? It is 2 pi FL, where F is 60 Hertz. So 2 pi into 60 into 0.1. So you get 6 into 2 pi, it is around 12 pi as XL. Simplifying this, we have omega square L square. So 4 pi square 60 square 0.1 square. After simplifying all these, we get cos phi approximately 0.3, because if you see all the 4 options, they are actually quite similar options, but it can be simplified. Approximately you will get the value as 0.3. The voltage of an AC source varies with time according to equation V equals 100 sin 100 pi t cos 100 pi t. Just I will change this pattern 2 times 50 sin 100 pi t cos 100 pi t. Suppose if I write 50 into 2 sin 100 pi t cos 100 pi t, this is in the form of 2 sin theta cos theta, that is equivalent to sin 2 theta. Theta is 100 pi into t. Finally, the expression will be sin 200 pi t. I have changed this equation as 100 as 2 into 50 sin 100 pi t cos 100 pi t, 2 into 50, 50 times 2 sin 100 pi t cos 100 pi t. This is 2 sin theta cos theta. So 50 into sin of 2 into theta, theta is 100 pi t, it becomes 200 pi t. If you use this equation, 50 into that, you get 50 sin 200 pi t. The peak value is 50. The angular frequency omega is 200 pi. Then omega is 2 pi f is equal to 200 pi. Cancel pi, 2f is equal to 100 and f is equal to 2f is equal to 200 and f is equal to 100 hertz. Primary winding of a transformer, this is NP as 100. Secondary winding as 200, NS is equal to 200. The primary is connected to an AC supply of 120. This is VP 120 volt and the current in it is 10 ampere here. So 10 ampere means here that IP value is 10 ampere. The question is voltage and the current in the secondary are. We have NS by NP is equal to VS by VP, where NS is 200, NP is 100. Voltage across secondary is not yet given, but voltage across the primary is 120. Simplifying this, you get VS as 240 volt. But if the transformer is ideal, the power output is always equal to the power input. Output power is VP IP is VS IS and input power is equal to VP IP. If you use this equation, you get VS by VP is equal to IP divided by IS. Substitute VS and VP because VS is done here and IP is given as 10 ampere and find out IS, which is equal to 5 ampere. A transformer is employed to reduce 220 to 11 volt. 220 is the primary voltage and Vs is the 11 voltage. The primary draws a current of 5 ampere, that is IP is equal to 5 ampere and Is is equal to 90 ampere. What is the efficiency of the transformer? See, efficiency is normally given by the ratio of the output power to the input power multiplied by 100. Output power is Vp IP divided by Vs Is divided by Vp IP, and substituting this we get Vs Is by Vp IP, 11 into 90, 220 into 5. So if you simplify this, this is 20 times, this is 20 times, 20 get cancelled, finally 90 will be left. This is 90%. This is the efficiency of the transformer, which is option D. So thank you students. I hope you understood the concepts of electromagnetic induction and alternating current. All the best for your exams. Thank you.